The isosceles triangle.
It's 4.5?
Yes, sir.
Yes, sir.
Isosceles triangle has one set of congruent sides. The one thing that might be a little bit new is how you would label an isosceles triangle. For example, guys, if I say that triangle ABC is isosceles, if I say that triangle ABC is isosceles, there's a couple of things that you can infer from that statement. One of the things that you can infer, one of the things that you should go with right away, is the fact that the second letter in that, the B, this is called the vertex angle. The vertex angle is the angle between the sets of sides. The vertex angle is the angle between the set of congruent sides. And that means your A and C are here. The reason why we define that is because a lot of times when they say that you have an isosceles triangle, they might not give you a diagram. Let's say, hey, triangle XYZ is isosceles. If triangle XYZ is isosceles, it tells you that Y is the angle in between the two sides. That's why we define it. Also, when you have those sides that are congruent, when you make your tick marks, notice how the tick marks are pointing towards what are called base angles. You guys ever heard that before?
Base angles?
Base angles.
Yeah.
They don't necessarily have to be on the bottom.
No, they just talk about
They're the ones that are opposite the sides that are congruent. So base angles are also congruent to each other. So an isosceles triangle, you've got two sets of, an isosceles triangle has one set congruent sides and one set of what are called, yes sir? Yes. And what happens here is that those base angles are always looking at the sides. So the angles always look at the sides that are congruent, no matter how you draw it. If those are my angles, those are looking at the sides, that would be congruent. The base angles, they're just called base angles, but they don't necessarily need to be on the bottom. They can be anywhere. You'll hear that term side opposite quite a bit as we go along. Side opposite angles and stuff. Which gets you to one of the things when you have isosceles triangle. Well, how many degrees are in a triangle to begin with? 180. Does that ever change? No. So what's nice is that if I know what angle B is, if I know that angle B in this case, let's say it's 35 or 36 degrees. That means angles A and C have to be the same angle and add up to equal 180 and put it all together. So it's super easy and super fast to work with. You take your 180, subtract the 36. What do you get? 144, I believe? Which makes both of those two angles how much? If we don't open the door and don't answer, will they go away? The way that the blinds are here and the way that this part's right here, all I can see is like, yeah, all I see is your hair just bobbing when you're laughing. So it's kind of like this.
Okay.
Oh, that spider thing was awesome. So you get 72 for your face. That's the kind of stuff that we're going to see, guys. We'll see a little bit of quick algebra like that. So. Which reminds me, I want to make sure that we put this in a square.
I'm not sure what's going on.
Basically, what I want to get at with a couple of these, listen to the definitions, is that when you're dealing with isosceles triangles, like I had mentioned earlier, there's a couple of things you're going to be able to infer. And this is one of those things. If you are given legs that are congruent, then you know you have base angles that are congruent. The base angles are always the ones that are opposite the legs. And it goes the same way going the other direction. If you have base angles that are congruent, then you know that you have legs that are congruent. Sides, excuse me. As you get further into math, we start calling the sides of triangles legs. Okay. I just wanted to make sure you had that on there because it is something that does show up from time to time. If you want to put in there about vertex angle, vertex angle is the one between. The vertex angle will be the one that's not congruent to the other two. Sometimes people put that in there just to have it in case the term ever comes up. But the main idea here is that if you've got a set of congruent sides, that means you'll have a set of congruent angles that are opposite those sides. And it works if you have a set of congruent angles, then you've got a set of congruent sides opposite. Okay? Not so bad? All right, so let's go to the next one. Okay, we all got this? I don't want to get ahead of you. I know some of this is so bad.
Yeah.
What about equilateral triangles? Next week.
Oh my.
What do you know about equilateral triangles? All the sides are equal. Not yet.
Wait, is that like a abbreviation?
Not really.
Oh my.
Equilateral triangles. Equilateral triangles have all three sides that are equal to each other. And if you go back and start thinking about it, the equilateral triangle is honestly just a fancier version of an isosceles triangle. Here's why. If I block this one out for a second, if I know that right now, I don't know what that third side is, but I know that I've got two sides of the same. I then know that I have two base angles that are the same. You okay with that? Now, if I cover up this side then, these two sides are the same, which means their angles, well, this angle has a single tick mark, which means this one has to have a. So what happens is, with an isosceles triangle, with an equilateral triangle, it is nothing more than an isosceles triangle, just fancified. Fancified. It gets all three. Yeah, I don't think it's a good one. It gets all three angles that are equal. And if all three angles are equal in a triangle, what do all three angles have to equal? How much? Same thing, which is 60. So all sides are equal, all angles are equal, and all angles will equal 60 degrees every single time you have an equilateral triangle. It never changes. Because how many degrees are inside of the circle? Inside of a triangle? 180. If all three of them have to be the same, you take 180 divided by 3 and you get 10. And that's why that works. Which gets us to the other idea of another if-then statement as far as equilaterals are concerned. Like we said earlier, if you had legs or sides that were congruent in isosceles, then you had base angles. Well, same thing goes for here. If you've got all three sides equal, then you're going to have all three angles equal. If you have all three angles equal, then you have to have all three sides. So let's go that together real quick.
Quavo.
Yeah, if you're worried that you're running out of space, flip over the progression sheet. Look, oh, there's another side. Well, you sat upside down. It would be upside down. It would be right side up.
Got me there.
Okay. Another way to write this is this. If all three sides are the same, then all three angles are the same. And again, like I said, it works the exact same way if you go the direction. If all three angles are the same, then it gets you all three sides. It works going both ways. And also, not a bad idea, angle equals 60. In equilateral triangle, the angle will always, always, always equal 60. That never changes. It'll never change. Okay. One other quick little definition that shows up from time to time is in this new textbook. They showed it a little bit early. They don't do a lot with it right off the bat, but it's one of those things that makes a lot of sense, and it's kind of like the basis of all trigonometry and why this next thing happens. So, when you have an isosceles triangle, it's not lame. If I have an isosceles triangle, and we'll call it X, Y, Z. I'll say that triangle XYZ is isosceles. If I say triangle XYZ is isosceles, that means where's your vertex angle? It's at Y. You're going to say between the sides. So Y is my vertex angle, which makes our two sides there and there. Okay. It also means that the base angles are congruent. But here's where things get kind of weird. If I draw in the angle bisector of the vertex angle, if I draw in the angle bisector of the vertex angle, what does that do to angle Y? Cuts it in half. Creates two equal parts. Okay? I had to give those two guys two tick marks because these guys on the bottom already had one. Well, what happens is that angle bisector, not only does it bisect that angle up top, but what it does on the bottom, it bisects this bottom part in the segment, and it's also perpendicular. Okay? And we had something that looks something like that a couple of times. What happens here, and this is kind of wordy, and I'll call this W. If the vertex angle is bisected, then bisector, the bisect segment, or bisector, I will call it the bisector, is also what's called the perpendicular bisector of the side opposite. And it's one of those things that looks like it's awful, but what happens here is that this, excuse me, this piece, it allows you, it basically opens up what's called trigonometry. Okay? What that statement does is that you're going to be able to take if I say that's equilateral, it is. Because I said it is. Squint, it looks fine.
Yeah.
That means my angles are 60. Is an equilateral triangle an isosceles triangle? Yes.
Oh yeah, it's a fancy one.
It's a fancy one. Okay? But is an isosceles triangle an equilateral triangle? No. It's like the idea that a square is a rectangle, but a rectangle isn't a square. Kind of. We'll get to that too. Don't worry. Okay. So if I draw this in, if I bisect a 60-degree angle, what do you get? 30. Okay. So this triangle here, this 30, 60, 90. And what will become, in a little while, an isosceles right triangle. If I have an isosceles right triangle, what do your base angles have to be? How much? 45s, thank you. So, and don't write all this out, but what happens here is that eventually, those four angles, 30, 45, 60, and 90, those four angles become the basis of trigonometry. Yep. This is called what's called the unit circle. Okay? As you go around what's called the unit circle, don't worry, this is not this year, this is next year. This year we start talking about these guys. These angles have a special importance second semester. These angles get reused then again next year, and then again the following year in pre-calc. Because as you go around this unit circle, what was it? What's 135? I always forget that one.
Oh yeah, it doesn't.
So what I'm getting at here, guys, ladies, gentlemen, what I'm getting at here is that the importance level on equilateral isosceles triangle, that little statement of a perpendicular bisector, opens up to everything being, well, if this is 30 degrees off, those are 30 degrees apart. These are 30 degrees apart. These are 30 degrees apart. Every one of those angles, whether it's in the first quadrant, second quadrant, third quadrant, fourth quadrant, has the exact same value. What changes is the signs. What I mean like that is positives and negatives. In the first quadrant, is everything, what are the signs for X and Y? When you're ordered pairs. Ordered pairs. Yeah, positive, negative. Which ones are they? They're both positive. When I move over to the second quadrant, what becomes negative? Third quadrant, they're both negative. Fourth quadrant. What happens here in trigonometry is that the ordered pairs that are here and here are the same. What changes are the signs. Here here. So all those values share the same ordered pairs. Their signs, the SIG ends, change as they go through. By working with trigonometry, it shows what's called, ever heard of a thing called oscillation? Not isolation. I wish we could isolate you.
Jeez.
Oscillating fan goes back and forth. Oscillation is a science thing.
Oh, it is.
Oh, that is scientific.
You have what are called sine and cosine graphs. As you go around a circle, dealing with those values, it oscillates throughout your ordered pairs. Everything you guys learn in geometry about equilateral isosceles triangles, everything you learn about this silly little thing about this builds. When we go into this next semester, we talk about right triangle trig, sine, cosine, tangent. Every single one of those things is important because it's getting to the end game. End of next year, when you get in a trig, you'll be doing this kind of stuff, and it all stems back from what I just said about having a perpendicular bisector of a 60-degree angle. Those things are all related. Just like when you guys learn how to do certain things back in algebra, it's related again now. It's related again later. It comes full circle. Sorry, that was a bad pun. But that's the idea. That's where this stuff goes to. See, when we talk about these things, there's reasons why we show you guys this stuff now, so you can build on it later. Also, then you can do stuff like this. Not a problem. Now this. You can do this. Ooh. So, I've really had it, Joe. Come on. When we get into stuff like this, it's going to allow us to be able to solve for x's and y's. You're right. It is all three different triangles. So when we look at something like that, you want to draw it the best of your ability, because Lord knows I would have a heck of a time drawing that myself. But if you get the idea of where you're going through it, and how does it set itself up? How do you use bits of each style of a triangle to solve a problem? Now, in this case, you'll notice you've got a right triangle, you have an isosceles triangle, and you have an equilateral triangle, one after another. Only one of those triangles is giving you enough information that you can work yourself out of. Which one of the triangles? The equilateral, the far right one. So I know that the equilateral triangle is on the right-hand side. It's VTU. Its side lengths are all 12. If this has a tick mark, this has to be 12. Okay. Now, when I go figure out what this side length is, well, what kind of a triangle is this? Does it say that it's 45? You can't. You don't want to make an angle side-side out of you and me.
Oh, yeah.
The reason that it's not a 45-degree angle is because there's no tick mark here. If there was a tick mark there, then it would be an isosceles. So you get that? So here's what happens. Guys, here's what happens. You've got the right angle here. What is the side opposite a right angle always called? Hypotenuse. Good. And then this is a 12, and this is our unknown. How do you find side lengths with a right triangle? You have all. Put that good there. Very good. Yeah, it's what the Pythagorean theorem. The idea of a squared plus b squared equals c squared, where this is your a, b, and c. Your c value is the one that never changes. The c value is always across the right angle. That will never change. The other two can be either or. You guys have all seen that at some point in time in your lives. This is one of those things that they assume that you would remember, kind of like adding and subtracting. You know, right equation of a line, that kind of stuff. You've done it. So you do this quick refresher and you write it out. Well, something squared plus 12 squared is 15 squared. Well, you guys have calculators. You press some buttons. right.
Oh,
And you get 9. Just by using the calculator and using the Pythagorean theorem. Again, that's one of those things that does not go away. Okay? That gives you that side length of RV equaling 9. You know that VU is 12. What's 9 plus 12? That gives you your Y value. You're halfway done. These big picture problems do take a minute or two to go through. You have to use multiple parts. Back to the angles. What does that square box mean? 90. What do all the angles equal in an equilateral triangle? 60. So if this is 90, that's 60. What does that have to be? 30. Very good. Now, how many degrees are inside of a triangle? 180. Inside of this triangle, we know that it is an isosceles triangle because you've got your tick marks here and here, which means your base angles have to be the same. So if I take my 180, subtract the 30, what am I left with? If both angles have to be the same, I just cut that in half and you get 75. And that's okay. There's nothing wrong with that. What's happening here is we're just doing a bunch of quick, simple math by using the properties of equilateral and isosceles. You'll have something thrown in from time to time with the Pythagorean theorem. But for the most part, it's nothing that's going to be earth-shatteringly horrible, difficult, bad. Okay? Let's try another one. Maybe stuff like that, yep.